All right, here's another one. Notice your eyes should jump right to these words. We're talking normal again. So this is a normal CDF. They give us the population here, which might be nice to know. We might not care. Scores are approximately normally distributed with a mean of 511 and a standard deviation of 112. Great. Estimate the number of students who scored 600 or above. Well, okay, that's just your regular old normal CDF. Should I write this here? Yeah, because when we get to the print version of this, you're going to want to see this on here. You know what? That makes me think I probably should have put this on here too. This was, just so you know, this was normal CDF. This one, okay, fine. The one here was 0.69. This one was fine. Normal CDF from, that's an F, negative 1.2 to positive 1.2. Okay, great. This one, I'm going normal CDF from, well, 600 or above. So I'm going from 600 on up to infinity. And but I can't just use the regular old standard normal distribution. I have to use this one that has a mean of 511 and a standard deviation of 112. Okay. And what do I get here? Approximately equal to normal CDF from 600 to infinity. This has got to just be the most exciting YouTube video you've ever seen in your life. 511 standard, just watching someone push buttons, like seriously. Okay, sorry about that. 112. Sorry, it just takes an extra second like that. So I'm trying to, like, keep you awake. All right, about 21.3%. Okay. Oh wait, I'm sorry. I'm supposed to find number of students. Okay, well I did that wrong, didn't I? I just found the probability that a randomly selected student is in that zone. Well, you know what? That's fine, because I need to know how many students there were. Well, I know 21.3% of them were above this score. Actually, I didn't do anything wrong. I'm just not done. So I need to find out what that is in number of students. 21.3% of these people. So I just need to take that times this super huge number, which is 1127021. Okay, great. And that's 240,518. Okay, great. Suppose you were to randomly sample 50 of them. Okay, so we're talking about sample, another keyword there to get used to. Sample means we're going to take a sample distribution, and the standard deviation changes when we get to samples. Remember, the sample standard deviation is this thing, and that's really important here. That would be the population standard deviation, which is 112, divided by the square root of the sample size, which is this. Just because we're going to need to know this, let's figure this out now. 112 divided by the square root of 50. And we get something like this, 15.8. Okay, the sample means are, of course, much more stable, I guess you'd say. The standard deviation among sample means shouldn't be as nearly as wacky as the standard deviation in the regular old raw data. So by sampling a size of 50, I change the standard deviation from 112. It settles all the way down to 15.8 because it gets divided by the square root of this. Okay, so what's probably the mean score of your samples between 500 and 520? Same mean. It's the sample means should also crowd around 511, but they're not as spread out. They only have a standard deviation of 15.8. So same thing. Normal CDF. Well, sort of same thing. Normal CDF. I want the probability. Yeah, it's probability. So remember, normal CDF just gives you a probability in the end. Between 500, so 500 is the lower limit, 520 is the upper limit. The mean is 511 still, but now the standard deviation of sample means, because that's the channel I'm on now, is only 15.8. Okay, the exciting part. Listen to me push buttons. Normal CDF from 500 to 520. If I go too fast, though, sometimes it just doesn't keep up, and then I got a real problem. Oh, by the way, I got the new emulator for the new calculator today. Oh, you know what? Since that's sitting there, I can actually do this. Ants. Don't have to type it. Nice. Okay. and I get something like 47%. That's about right. I mean, you expect it to be kind of high because in this zone from 500 to 520, it includes the mean, so it includes the peak. So it's going to be a pretty hefty probability. 7.14, I don't know, something like that. Okay, good. You feeling good about this? Gosh, the more videos like this I make, the more it feels like I'm actually having a conversation like you're actually here. Is that weird? I guess it was bound to happen sooner or later. Oh, we can't see this whole picture. I'm sorry about that. You see it all now? Yeah. Sort of. Okay. The graph below represents a normal probability distribution. Okay, there's your keyword. Oh, I should start doing this. This looks a little more... Yeah, okay. Probability distribution with a mean 25. Okay. And standard deviation 2.5. So as I go 2.5 this way, I hit the inflection point and so on. Estimate the area under the shaded region. Well, it looks like this is probably going to negative infinity, which is really not much after, you know, below 17. It's normal. The mean is 25. Standard deviation is 2.5. I got everything I need to plug this in. This is a lot easier than the last couple of questions. I don't know why it's in this order on the test. On your test, also, it's not going to be in a predictable order. This sort of thing may happen, so I guess this is good. Lower limit, let's go negative infinity. Upper limit looks like, whoa, that's a 9. Upper limit looks like it's supposed to be 21. Mean here is 25. Standard deviation is 2.5. Let's just plug that in. Normal CDF. From negative infinity. I mean, if I put 0, it's probably just as good as negative infinity. That's what it looks like. Up to 21. Mean 25. Standard deviation 2.5. And if I typed all that right, it's about 5%. And I don't know if it looks like that to you. 5.48%. Approximately. That's 5% of this whole area. That looks about right to me. Alright, I don't know about you, but this is going really well. Alright, a coin is tossed 14 times, comes up tails twice. Well, that's kind of unusual. State a null and alternative hypothesis. I don't think I would ask it like that. Again, I'm in good with the test maker, so I can be pretty good about that. You know what? Gosh, can you watch me type? That might be more fun than watching me push buttons. H sub 0 is... Let's make this so you can see what I'm doing. And they always say null hypothesis, you know, it looks like that. Really? Can I just do this? Oh, look at that. Sound effects help. The null hypothesis, I mean, even if I don't ask this question, it's good to know what we're testing here. Null hypothesis is about the fact that nothing weird is going on. The coin is fair. Like, the coin was supposed to come at 50-50. The alternate hypothesis is that there is some funny business going on here. That something, you know, things aren't the way they seem. The coin... does not come up tails as often as it should. Or I could say something like, it's unfairly not tails, or it's unfairly heads. How about that? The coin unfairly favors the heads side. Okay, great. Yeah, the typing is a lot faster and cleaner, actually. It looks nicer when I print it out. All right, can the coin be considered fair at the blah, blah, blah? All right, so this is, now here's a question where, should we use normal, should we use binomial? Well, coins were kind of the poster child example for binomial because it's success, failure, it's heads, tails, it's yes, no, it's right, wrong kind of thing. So yes, this is a binomial. I'm going to use binom PDF to produce the list of all the possibilities for 14 tosses of a coin. So I'm tossing a coin 14 times. The chance of success is 0.5, and we'll say that's for tails. I'm going to store that as a list. Now what that's going to do is it's going to produce a list in my calculator of all the different probabilities of what if I, you know, what's the probability that exactly 0 of those are tails, or 1, or 2, or 3, all the way up to all 14 of them being tails. And it's going to store that in a list. Now what I need to do here to test this for fairness, I think, I'm trying to find out really, is 14, no, not 14, is 2, is, the question here is, and this is what they ask you here, this is why they ask you this for A, is only 2 tails too low? That is the question. This is weird on the low side. So I want to add up 2 plus, and this is the part people get wrong, plus anything weirder. This is why I didn't just figure this out for 2. I don't want to know just the probability that is exactly 2. I want to, like, if, say I was going to argue this in court. Say I'm trying to convict this coin of being unfairly on the head side. I'm going to say, well, look how weird it is that we got 2 heads, or even I'll even give you what if we had 1 heads, or what if we had 0 heads. How often should it come up as weird as only 2 heads? So 2 or 1 or 0. And we're going to try to test that and see, is that less than 5%? If it's less than 5%, we have a case here. Oh, I'm sorry, 1%. If it's less than 1%, then we can say, well, that's beyond our tolerance for weirdness. So let's do that. Let's figure out the binom PDF. I'm jumping to it to save some time. 14 events with a half chance of probability success. Storing that as L2. It's going to produce my list of 15 objects from the 0th one down to the 15th one for 14 successes. Remember, the top row is for 0 successes. That was a pain. And I'm going to add up P0, P1, P2, which in this list is actually that number plus that number plus that number, which is called, this is called L1. Notice how it's called 1. That's the first, second, and third. So I'm going to add up the first, second, and third members of this list. So go to list, sum the first 3 of L2 from the first one to the third one. That's for 0, 1, 2. And it's, yeah, it's way, well, it's not way less. It's almost, it's over 0.5%. But it's, this turns out to be 0.006, which is less than 0.01. So we say too weird. We cannot reject, so we can reject, sorry, we can reject the null hypothesis. All right. Give the inflection points for the graph of blah, blah, blah. Well, you look at this and go, oh my gosh, what am I supposed to do with my calculator now? Well, don't do anything in your calculator. Take a breath. It's going to be all right. This is the standard normal curve. Am I going to throw one at you that's not parent and not standard? I don't think so. Like, they had one in the worksheet that had like a 3 here, or didn't have a pi here, and there was like a 3 here. Something really crazy like that. No, you're either going to get this one to the parent, so you just kind of have to know the difference, like I was saying before in the other problem. This is standard. So give the inflection points. The inflection points are, well, hopefully where you'd expect, which is exactly 1 and -1. That's it. Give the inflection points. Do they want the y coordinate of that? I don't think so. They mean when x equals, when, sorry, z. When z equals 1 or -1. That's all I want for that. All right, and that's it for the... Really? That's it? Oh, yeah, because I took out a bunch of them that are from 10.8, which we didn't do. So that, I mean, technically there's only, I don't know how many questions now, because I took off 2 or 3. There's less than 11. Problems from this thing that are like your test. So I had to supplement. I mean, I can't ask you a question. I can't give you a test that's the same length as a quiz. So yeah, I thought I'd ask some more. There's some more multiple choice in there, and there is a question like one of these form C's. I'm not going to tell you exactly which one. I'll tell you right now, I don't really like this one because it's too heavy on knowing something about baseball. Kind of like there was that one where I really hated to have all the helium science stuff with the membrane and the helium molecules. It was way too sciencey. This one's kind of too sport specific. It's a good problem, but I don't want you to get so confused about baseball that you can't answer this question. So we'll say, all right, in baseball, success for a batter is blah, blah, blah. Well, right here, when you see a word like success, you should think, okay, we're talking about success. We're talking about probability. It kind of looks like we might want to do binomial, because binomial was one about success failure. Normal was the one about what's the value of the statistic, like how many cars do you have, or how much does your luggage weigh. I mean, it's a number answer rather than sort of a true, false, success, fail kind of number. These success ones are going to lead me to think, you know what, this is probably one of these, or a neither. I mean, if it's just asking about mean and standard deviation, maybe it's not even this, but I'm thinking more of this right now than I am normal. All right, I've only got a minute left. Can I tackle this in a minute? Perhaps. After having read the problem more carefully, I don't think I can, but okay, here's a little bit of justification why I thought it might be binomial, because there it is. What this is going to look like, though, is I'm going to have a... Let's go ahead and actually use 27. And binomial probability distribution for your choices. We're going to have one of those graphs that looks like number 1 from the first part of this test. I'm going to stop here before I get too far into this problem, and I'll start here on part 3.